presentation, the context and key objectives of Task 3.2 will be introduced briefly, a key component of the PVOP project. This task focuses on the energy management and control aspects, and in the following minutes, it will be shown how this challenge is being addressed. The main objective of the task is to develop and implement advanced energy control systems to maximize the operational efficiency and commercialization opportunities of our battery hybrid PV plants. This is crucial to optimize both energy generation and its economic value in the market. PV installations offer energy independence, reduce operating costs, and significantly reduce carbon footprint. But, as it is well known in the solar power industry, its benefits are limited by daylight hours. Through battery energy storage systems, these limitations are overcome, making a variable energy source controllable and manageable. Hybridization is key to the operational flexibility and reliability of the energy supply. The combination of solar generation and storage promises greater flexibility and cost effectiveness, but it also introduces new operational and commercial challenges. How to operate the battery system to decide when to charge or discharge the energy? How do we maximize clean energy consumption considering market prices? How to take advantage of market prices or avoid penalties for deviations? An agent in charge of managing the energy flow of the different energy sources becomes evidently needed in order to avoid wasted energy due to poor management, penalizations for excess power, missing out on arbitrage revenues or grid services, failing to meet dispatch commitments or grid codes, operating suboptimally in the face of dynamic market prices. An EMS is crucial for minimizing the levelized cost of storage and maximizing profits by optimizing operational efficiency, enabling multiple revenue streams, ensuring regulatory compliance, and providing advanced analytics for maintenance and performance improvement. The system will act as a slave node in the energy network. It will integrate all smart devices within the photovoltaic system, allowing them to be monitored and controlled from a single location. The backdraft EMS will receive inputs from sensors, electricity prices databases, meteorological databases, and electricity market analysts in order to compose the best operational decision at all times, achieving an intelligent management of the available energy, thus maximizing profit and reducing the return of investment time. The EMS system must be self-contained and be equipped with the intelligence necessary to dynamically coordinate the operation between PV and BESS to maximize the performance and energy trading of the plant, optimize revenues through arbitrage strategies, market price monitoring, and grid services, comply with technical and contractual restrictions, dispatch curves, minimum SOC, ramps, peak power, consumption, etc. Integrate predictive models, weather, prices, consumption, for an intelligent and proactive operation. Enable active participation of strategies in electricity markets. Establishing the new frontier in energy technology to turn solar power hybrid facilities into a flexible and monetizable asset. There are different operating modes contributing to generating revenue stacking for hybrid PV plus battery energy storage system through the strategic utilization of multiple revenue streams and cost-saving opportunities that will lead to a quicker return of investment. In this project, the following control strategies will be addressed. Intelligent maximization of self-consumption. This mode ensures that energy generated by a solar photovoltaic system is used as much as possible on-site rather than being exported to the grid at lower rates. The BESS stores excess solar energy during the day and uses it during night or low generation periods, which the system can anticipate based on received data. Time of use or arbitrage involves charging the battery during off-peak hours when electricity prices are low and discharging during peak hours when prices are high. This process allows the BESS to capitalize on price differentials by buying low and selling high. Peak shaving reduces the demand charges and electricity bills by lowering the peak demand during high consumption periods. By discharging the battery during peak times, businesses can avoid the highest tariff rates associated with their peak usage. Demand response allows BESS owners to receive payments for being available to reduce energy during high demand periods while maintaining normal production operation. Microgrid mode, also known as island mode, it allows battery disconnection from the grid and continuous autonomous electricity supply with previously stored energy. This capability not only improves energy resilience, but also protects sensitive equipment, ensures the operation of critical services, and reduces dependence on the grid at times of instability. Initially, the EMS will be deployed in a controlled test environment. This will allow us to truly validate its functionality, performance, and robustness under various operating conditions, ensuring its reliability prior to actual deployment. Subsequently, the EMS will be implemented in full-scale industrial hybrid PV and battery plants. This final phase will validate its ability to optimize energy management, maximize benefits, and ensure operational integration in a complex and dynamic real-world scenario. For more information, join the PVOP project and do not hesitate to contact us in the indicated addresses.